Hello, thanks for watching this. This is a re-recording of the presentation I gave at the Metal Earth meeting on February 27th of this year. My name is Christopher Mancuso. I'm a PhD candidate at Laurentian University. I study geophysical inversion, and that's what this talk is about. This talk is about a specific method called joint inversion. It's a joint inversion of gravity and seismic information that we're going to be doing to resolve the region around the Sturgeon Greenstone belt in the western Wabigoon area. So the impetus to do this lies in the inherent limitations of geophysical inversion methods on their own. These limitations are unique for every sort of data that you collect. And in the Metal Earth project, we're really familiar with three sorts of data sets. We have reflection seismic images, we have magnetotelluric imaging, and we also have ground gravity data. And I've highlighted that in red because that's the particular data set that we're going to be focusing on as part of this study. And ground gravity data is very sensitive to mass distribution and across particularly lateral distributions, but it can become quite unreliable and it's prone to something called non-uniqueness. So in order to try to overcome that limitation, we need to constrain it with some other information. And the constraint that we're bringing in this case, is seismic refraction data. So this is the study area. We're going to be looking around the Sturgeon transect, which is here at LN331, which traverses the contact between Winnipeg River and western Wabigoon terrains in the western Superior Craton. You can see that it also overlies the Sturgeon Greenstone belt itself. What's shown on this image is some of that constraining information I talked about, that refraction information. So these red dots are source points for wide-angle refraction surveys that the Lithoprobe National Research Project did in the early 90s. It's done in two lines, two profiles. There's an east-west profile that courses this way and a north-south that courses this way. And these were designed to study the entire lithosphere. That's just zooming in on the traverse. And again, those source and receiver locations for the Lithoprobe wide-angle data set are shown. And this just emphasizes the close proximity of that information, particularly where they cross with regards to the Sturgeon transect, as well as the Matabele transect down here. Also shown here is all these blue dots. Those are the ground gravity stations we have in the region, provided through the GSC compilations. And the traverse itself, which is comprised of Metal Earth ground gravity stations that are spaced 300 meters apart. So I'll give a little bit of an intro on what joint inversion is. And in this talk, we're going to be referring to simultaneous joint inversion. So that's where two distinct data sets are inverted at the same time and are fused in some way so that they have a common result. And so that fusion needs a structural or a link of some sort. In this case, we're choosing a structural link where the shapes in one of the inverse models will try to inform the shapes of another. This has the advantage that we don't need to really rely on some sort of empirical relationship between things like density and wave speed that we might not be able to estimate or approximate at depth in the Earth. So the objective function for this scheme has 5 parts which need to be optimized. The first 2 are the data misfits for each the seismic tomography model and the gravity inverse model. That third part is that structural link. And so in this case, we're using something called a cross gradient technique. And the fourth and the fifth parts are linked. They trade off with each other. And the regularization function, or regularization parameters. So in any inversion, you need to regularize the model output to be more smooth in order to make it more geologically realistic. Otherwise, they'd be quite rough. Now, when you're doing with 2 inversions, you need to relax the smoothness of one model to allow the other model to conform to it. And so in this case, we can force that smoothness on the gravity or on the seismic or both together in various weights. And that's weight is what we're going to refer to as the alpha parameter in some of our results. So there are 2 main goals to this study. The first is to get a density volume of the region around the Sturgeon Greenstone belt. And we can do that by doing regular single property unconstrained gravity inversions. But those will serve as a comparison to the joint gravity models that we're going to make. And that's using that seismic information to help constrain that. The data set that will be involved is that regional GSE ground gravity data and that lithoprobe seismic refraction information. The metal Earth gravity stations also exist in that region, but we're going to hold them separate from the actual inverse process and use them as a validation data set in order to have a quantifiable result. The second goal is crustal thickness modeling, and this builds off of the density volumes that we create in part A. But with this, we can estimate the bottom of the crust or the upper mantle lower crust contact. And we have some comparative data sets for that as well. We can use our own reflection seismic, but also we can look to literature for compiled teleseismic soundings on the MOHO. This is just how we prepared our gravity data. So it falls into two main sets. One is our inversion data set, and that's a regional GSE ground gravity data that I pointed out in the map earlier. That was spatially thinned to a resolution of 15 kilometers, reducing it to 86 stations, and that's just to prevent bias in the data. And our validation data set is our metal Earth ground gravity, and that is this orange line that's shown here. Our seismic information came from shot gathers and picking first arrivals of diving and refracted P waves. So in this image, you can see the information sorted by offset for different receivers. And then the first part here of pick the diving waves. So those are those first arrivals that don't refract off everything, that scoop down and return up to the receivers. And at later offsets, you can see that they start to arrive a little quicker at an increased rate. And those are those which critically refract off the blowhole. And they're best seen over here in this example on the left side. So our model space is interesting. Ideally, we would try to do this as an all-in 3D model using all information at once. However, there's issues when we look at the lower crust upper mantle contact, particularly regarding anisotropy. So the wave speed of the upper mantle increases in the direction of plate motion. So all the information we collect in the east-west line is going to have a different wave speed than that we collect in the north-south. And without any anisotropy parameters in the framework of the inversion, it's really best to deal with this into two data sets. So we've decomposed this into two model spaces. That being said, the density model space is uniform for both. So what I call this is two quasi 2.5D because they're very narrow, although we do them as 3D problems. So we have this north-south quasi 2.5D space overlaps with the density area here. Quasi 2.5D space around east-west, again overlapping. Where we'll have the most information is where the most overlaps occur. So we have a good overlap here between the density and velocity model that's running east-west, and a good overlap here where it runs north-south. And then we have the most overlap where both models meet here on the northeastern aspect of the Sturgeon Greenstone belt. All right, so here's some results. So what we're seeing in here is representations of different part of the objective function I showed earlier. So we have misfits for the seismic tomography, with each iteration inversion, misfits of the gravity inversion, again shown here. And then our structural enforcement across gradient shown here on the right. So we ideally want all this to minimize. Why there's several lines in each is these trade-off parameters that we're testing for regularization. So that alpha parameter changes with each of these. And you can see that, I'll point out quickly that there's the biggest change obvious is in the gravity information. As we lean the model very much towards, a density-driven solution, we have quite a bit different fit than if we lean it towards a velocity-driven solution. And that's the same for both the east-west and the north-south belts. But looking at the validation data set, we can begin to actually understand if the joint inversion process is in any way comparable to the single property on its own. So this is the forward model data from using the different outputs of the models from all these various joint inversion tests, as well as a single property, which acts as our null hypothesis in this case. So the single property gravity inversion is drawn as a red line in each of these. That's for the north-south belt and east-west belt. And very generally, you can see that between all the different tests that we ran in in the north-south belt, there was a very minimal difference, basically non-significance was observed between using joint inversion and single property in this case. However, that doesn't hold true in the east-west belt. In the east-west belt, there's very clear, obvious differences between using joint inversion and single property, in that the misfit, shown here as squared error, is up to 14% lower in many of the areas that along the transect, localized to some spots. For instance, right here up to the contact between Winnipeg River and the western Wabagoon, there's a significant decrease in misfit by using a very very velocity-driven solution to help constrain our model. We can demonstrate this in some of the slices of the models themselves. So this is the density model outputs from joint inversion. I've sliced them at 40 kilometers, which is the approximate depth of the moho. And just to kind of show the mass, and this would be sort of a representation of that contact of the lower crust. The black line in each is just the transect, just to orientate you. And the red lines show where that density model overlaps with the velocity model. So in between these red lines is where the velocity model was also calculated. Very generally, as we increase the alpha parameter or make the model more density driven rather than velocity driven, you can see that some of these features become smoothed out, like these errant rays, for instance, that probably picked up from the tomography. However, the density model becomes more coarse. It becomes quite coarse here. And some of the anomalies that are picked out actually become more loculated and pronounced, whereas they're smoother when you add more velocity information into it. I've starred on here the optimal model. That's the one that had the best fit in the validation data set, and that was the one that was the most density driven. However, again, in the east-west model, we found that the velocity-driven solution was the best fit. And you can see that smoothing of the mass distribution is very pronounced in here, where it's sort of a single entity here and with an isthmus, whereas as you continue to bring in more density information in the weighting, it becomes, again, these sort of separate root-like structures, roots and humps, and, loculated anomalies. And again, I've just starred what the optimal one is. So in this case, what would be most comparable to just gravity information on its own is quite a bit different in the case of bringing in velocity information. The second aspect of results is that crustal thickness modeling I mentioned, and I'm just showing the crustal thickness estimates we get from doing single property inversion, that bring in that north-south belt, and also the east-west belt. And you can see very quickly that there's very little difference between the thickness of the crust between these two. The distributions are very similar, right? But in that east-west belt, things become more continuous and smooth. We can compare the results of these models with the teleseismic information we have in literature, and that's what I'm showing here. I picked the best model from joint inversion, that one from the east-west belt, and showing here on the right, and on the left is the single property. It's a very sparse data set, but so I didn't really want to overinterpret it. But what I did is I put a line of best fit at that average moho depth. So that's just at 40 kilometers fit on both of these here. And just to give a general trend of the area. And you can see that it does seem to conform with the trend of the information that comes in the models themselves, particularly more so in that which has a little velocity information, in which that sort of isthmus is aligned structurally with this line of best fit. We can also compare with the reflection seismic information. So here's the Sturgeon seismic reflection seismic section. It's been enhanced just to help bring out some of the structures at depth. And on here, I'm just pointing out where I believe the moho exists on these seismograms. So here at 40 kilometers, and again, it's picked up here. In the middle, it becomes a little less clear, and it could be interpreted as a change in the depth of the moho or noise. But when we overlap the results from our modeling, you can see that it does seem to conform very closely to our model depths in here and here. However, that in this part here where there's information's lacking in the reflection seismic, it looks as though the moho has been modeled as continuous through here. So there's no pronounced change. I'm showing sort of a 3D image where you have to look through. And if you look through the reflection seismic at this sort of prominence here that's behind it, you see that there is a change in topography offline, but in proximity to the line. And these sorts of offline structural changes can often introduce noise into 2D reflection seismic imaging. And so this may provide an explanation for why there's less coherent reflections in this middle part of the seismogram. And that would be due to things called sideswipe and cross-dipping reflectors, introducing noise into that particular part of our seismic survey. So in conclusion, we can state that the joint inversion in the east-west belt case significantly improved the validation data fit. These improvements were localized and most prominent at the contact of the western Wabigoon and Winnipeg River terrains, and they're also more localized to the area where the velocity model overlaps areas of gravity extremes. With respect to crustal thickness, our model depths do seem to correspond to seismic reflections, and they also correspond to the teleseismic information. I would say that the structural changes noted in the joint inversion models more closely correspond to the southwest northeast trend that's supported in the teleseismic information. And that's everything I have for this talk. And yes, thanks for listening.